So, all right, let's get cooking. I'll try not to cough on y'all. I don't have COVID. I have really bad allergies. I'm currently have a Ricola in my mouth, so I'll try not to I'll try to turn the mic off. But please forgive me if I have some issues. But we're going to talk about Kubernetes for a long time. They gave me 90 minutes. I feel for y'all. And so the idea here is if you've never seen it before, but we're going to introduce what it is and get down and dirty and talk about a lot of stuff, the internals, how it works, how scheduling works, how containers get pulled and distributed and things like that. And so most of the demos, or all of the demos will be available to you. And pretty much any Kubernetes platform you can run these on, except for some storage stuff. And we'll talk about why storage is interesting and challenging when we get to that point. Who has Docker Desktop installed on their laptops? You have Kubernetes on your laptop already. You're a checkbox away from that. And I'll show you that when we get to that point. So that's me. There's my contact information. I work at a company called Pure Storage. We do really cool stuff with really cool technology. I focus on SQL Server and Kubernetes. There's my contact information. I'm on Twitter a whole bunch. The blog has recently been relocated to nocentino.com because of the previous reason up top. I work for a company now. GitHub, I'm a Pluralsight author. Today's content is based a lot off of the stuff I've done on Pluralsight. If you want 30 hours of deep dive Kubernetes funness, hit me up and I'll give you a free code. So not a sales pitch, but I want you to have access to that content. So when you leave today, the recordings for today will also be available. I've written a couple books. I've written a book on this exact topic of running SQL Server on Kubernetes, which was really fun. My co-author, Ben Weissman, and I wrote that book, and also a book on Azure Arc-enabled data services, which is what I think, rookie mistake there. It was one of the reasons why Microsoft has invested so heavily in Kubernetes, and one of the reasons I have is because they're starting to build their next generation platforms on top of this platform, and we'll talk about all of those reasons why today. So we're going to introduce what Kubernetes is. We're going to talk about why. That's a big reason. Then we're going to get into the Kubernetes API objects. One of the powers of Kubernetes is you get the right code to do stuff, right? And most of y'all are probably familiar with this with deploying things in a imperative way, but Kubernetes shifts the model and does things in a declarative way, and we'll talk all about that. Once we learn about the things that we can build, we'll look at the cluster itself and kind of the architecture and how things are laid out. Then we'll just get busy deploying applications. We'll do a stateless application. I can deploy Hello World at cloud scale, and I can also deploy SQL Server on Kubernetes. I wrote a whole book about it. So anyway, also questions throughout. So if something, you want to dig a little deeper into something, just raise your hand and we'll get into all that. And I'll try to manage the time, which I'm generally really bad at. So clearly Chrissy is here, right? She's awesome, by the way. If she was actually here, I would just put a video on and go watch her session. Anyway, so Kubernetes is a container orchestrator, right? Who's worked with Docker, right? So the last thing that you're going to do inside of a data center is run to your servers and type Docker run to stand up your applications. That's not quite very efficient, right? And that involves you doing things. Well, I jokingly like to say that Kubernetes has one job. It starts containers on nodes in a cluster. What I mean by that is it literally will start a container on some sort of compute resource where you have compute, whether it's in the cloud, on-prem, whatever. So a pod is your container-based application. It's a wrapper around the container or containers that you want to deploy in your app, and we'll get into all the gory details about what that means. One of the cool things about Kubernetes is it provides an infrastructure abstraction. So where we have this Kubernetes API, which we're going to introduce in a little bit, you can write code against that API and then consume the resources of your cloud or data center. So you'll find things like the ability to consume networking, storage, and then obviously compute when you distribute or deploy applications. One of the cool things about it is this idea of desired state. If I say, hey, Kubernetes, run this application, maybe keep 3 copies of this container running in my data center, its job is to keep those applications running in that state. If I shift the state of a cluster to deploy new or more replicas of a particular application, it will move me towards that state if the resources are available to do the things that I want to do inside of my cluster. And so we're going to write code, right? Which is awesome, because then you can take that code, you can check that code in the repo, and then you have the state of your application available to you in a very well-defined way. So the number one benefit of Kubernetes is it, like I said earlier, starts containers on nodes in a cluster. What I mean by that is it will literally start the container on a server wherever you have, so VM, physical, whatever it is. It has the job of managing state, so when I tell it to do a thing, it's going to start that thing up and then keep that thing up. So if we skew from the desired state, maybe a node crashes and all of the pods that were running on that node are no longer available, well, it's going to figure out somewhere else in the cluster to run that workload such that I stay in a desired state in my application. It provides networking and services. So with all of that change that I'm talking about, things kind of scaling and moving to and from the desired state, one of the things that we don't want to have to do as developers and administrators is keep track of where those things live in our cluster from an addressing standpoint when I distribute workload to access the applications that are deployed. And so we'll get a networking abstraction that says I can send my traffic to this IP, and Kubernetes will load balance that or route that to the particular pods that support that application. We'll get into all the gory details of that today. It also provides load balancing. So if I do have an application that can scale out, have many copies of an application, it will distribute the workload or the requests to that application for me. And I don't have to have any super high-end load balancing things to do those things. It comes for free inside of the cluster. It does integrate with more sophisticated load balancers if you do need that. Persistent storage is always fun inside of Kubernetes, but we'll talk about that later, about the funness, but I can ask a cloud or an on-prem system to give me storage to attach to a persistent state application, like SQL Server. And a declarative model, again, because we're going to write code to do the things that we want to do, and I can share that code with you so you can build the application exactly as I've defined. And that's one of the powers of things that Kubernetes provides to folks like Microsoft. Microsoft built Azure Arc-enabled data services. I write some code, and I can deploy a SQL MI wherever I have Kubernetes. It could be on-prem, it could be in the cloud, it could be in Azure or AWS. It doesn't matter because that code describes what I want. Kubernetes does the placement of that application inside of my cluster and consumes the resources of my data center to give me access to that thing, right? Something as sophisticated as a PaaS offering, like SQL Managed Instance. And so when we're talking about Kubernetes, we have this thing called a control plane. That's kind of the mechanism that coordinates the work inside of a cluster. And there's 4 primary elements of this thing that is the control plane. Is the API server, the cluster data store, the scheduler, and the controller manager. Sorry if that's a little tiny in the back. But that API server is the thing that's going to be a stateless application that represents the objects that I can consume from the cluster. When I say objects, really it's the tools or the building blocks of my application, right? And we'll get into the types of API objects in a minute. The primary way that I'm going to interact with my cluster, which we learned all about yesterday, kubectl, right? I say kubectl, it was fantastic. Like I was like busting that guy. He never actually said the name, which I thought was even better, right? Anyway, so kubectl, kubecontrol, kubectl, and all of the variations that we learned about yesterday is the primary CLI tool that we're going to use to interact with the API server to do things like get information or change state, like deploy an application, okay? The cluster data store is a persistent data store. It's a key value data store that holds the state of the cluster over time, right? And so if I put a workload in there, the API server just serializes that object and stores it in that key value store for the persistent representation of the state of the cluster. The scheduler has the responsibility of distributing the workload or the pods to the nodes, the compute resources in a cluster. You'll have one or many nodes to support your actual application workload. And then the controller manager has the responsibility of keeping things in a desired state. So if I deploy an app, the controller manager will take the cluster and drive it towards the desired state, deploying pods, creating services, and things like that. Yeah, it's a fancy interaction there. So generally speaking, kubectl talks to the API server over HTTPS and JSON. Good news is we don't have to talk JSON. We get the luxury of using YAML. And so we'll be able to write YAML and deploy applications that way, and we'll get into all of that. The worker node itself contributes CPU, disk, and RAM to the compute resources of your cluster. So you're going to have one or many nodes or worker nodes supporting your application workload. Who's built or designed like a VMware cluster? All right, so about 3/4 of y'all. Again, in the VM world, what does an individual node bring to the party? CPU, disk, and RAM, right? So you can put workload on it. So from a design standpoint, it's effectively the same thing. You're going to have as many nodes as you need to support your application, and those nodes will be as big as your biggest application to run on that thing. And then you'll do n+1 or n+2 redundancy for the number of nodes that you need to have in the event that a node dies, network partitions, or whatever badness happens that you want to protect against, right? The node runs this thing called the kubelet. The kubelet has the responsibility of talking to the API server to find out the state of this particular node. Kubeproxy has the responsibility of working with IP tables, thank goodness, to make sure that we don't have to do things like all the cool networking stuff that I talked about earlier that actually happens for us inside code. And then the container runtime has the responsibility of actually running the workload, right? And so historically that was Docker, now it is a thing called a container D. There's other types of container runtimes available, but brain work. The community has settled on container D. You'll see a lot about Docker deprecation. That doesn't mean Docker images won't work inside Kubernetes. The community, the technology ecosphere of containers is settled on this thing called OCI compliant images, or Open Container Initiative, I think that's what it's called, which is a defined structure of what an image or a container actually looks like, right? And so a container will look like this regardless of the container runtime that you're running. So you can produce images with Docker and they'll run in container D in a Kubernetes environment, no big deal. In fact, Docker just calls container D. Docker really is tooling to create and build containers. But if you look at like a process listing on a Linux system that is running Docker itself, you'll just see a Docker process that's called a container D process, that's called a run C process that actually created your container, right? And so those layers make up the how a container is actually built. Yeah, so container runtimes doesn't have to be Docker. So let's jump ahead. So the API objects, right? We have that thing called the API server, but we want to build stuff and deploy apps. And so that's where these API objects come in. So they represent the things in your system or the resources available in your environment. So pods are going to be your container-based applications, right? Controllers are going to be the things that maintain your desired state. We're going to focus on today what's called a deployment controller, and a deployment controller will create a workload or an application that we want to deploy in our cluster, right? And then services are going to be persistent access to our applications. So if I deploy 10 pods on my cluster, I don't want to have to keep track of where the 10 pods live to send workload to it. Kubernetes will provision a persistent IP and DNS name for me to send traffic to, and then it will distribute the workload for me, which is really super fabulous. And then storage. And so these are kind of the core building blocks of what you'll use to build an application inside of Kubernetes. There's a lot more than just this, but these are the core ones that you're going to use. There's different types of API objects for all various things. Jobs, honestly, would be one that would be interesting to y'all in that I can create and schedule jobs inside of Kubernetes, which would be something that just runs to completion and finishes a task. So back up a database server, run this script, versus doing something persistent, like running an application over time. Cool. Any questions or comments, team? Anybody want to get more coffee? Awesome. Oh, excuse me. Yeah, that's where we're going right now. I'm going to each one of those primary topics, those building blocks, we're going to dive into each one of those in more detail right now. Cool. So a pod is one or more containers. Who's deployed a container? Like just Docker run, yada, yada, right? Okay, so a pod is a wrapper around that, and I can add configuration to describe what I want that container to do, right? And so we don't generally deploy an individual container in Kubernetes. You deploy a pod, which runs a container, and that container has configuration and state, and that's held in the pod object. But in the end, it's really just your application. It's the most basic unit of work. It's the thing that's scheduled. All a container is a process, right? If you look at the bowels of what a container image does, and we'll do this a little bit later, it's just an executing process with an isolation boundary around it. And this is going to sound weird, or not like weird, not like all like clouds and arrows. But eventually, Kubernetes will become the operating system of your data center, because all it does is starts processes on containers, or starts processes on operating systems available in your data center. And then consumes the resources of your data center, like networking and storage. It's the unit of scheduling. So when I say I want to start a pod's going to start somewhere on a node in a cluster, and the scheduler has the responsibility of making it happen. It's ephemeral, which is a little bit weird from a concept standpoint, is that no pod is ever redeployed or recreated. And I will mess this up throughout the entire session when I talk about deleting pods. I'm like, oh, they got recreated. It doesn't. There's no state maintained between one execution of a pod. If it dies or fails, it's gone. A new one will come back with the same configuration, which has an interesting effect. And when we start building stateful applications, you would think that'd be kind of debilitating how I would maintain state over time. It actually becomes quite liberating, because now I've decoupled computation and state. right? We'll get into all that nerdiness later. Cool. So controllers have the responsibility of creating pods for you. Generally speaking, you won't go and create pods. You will create a controller. That controller will create that for you and manage that state, right? And so that idea of, hey, I want to start this application 3 times in my cluster, that's the responsibility of a controller, right? And we're going to focus on deployments today. They respond to pod state and health. Who was in the session yesterday that I did? Okay, about 3/4 of y'all. When I deploy an application, you saw like 0 of 1 and ready and all that fun stuff. And I wouldn't be able to give my controller a little bit better understanding about the health of my application, right? And so that's where the things like probes and whatnot came in. And so I'll describe in my deployment what my application does. It's a web server, it has this URL, check that URL, and if that goes down, then maybe I kill that pod and deploy a new one, right? So then I can start building self-healing applications that can respond to the changing state of my health of my application, right? Which is really great because then you don't get paged, right? Yeah, precisely. So the comment was treating it like cattle. This is actually exactly that. So I've used the term deployment a couple of times. A deployment describes what I want to deploy. A deployment creates a replica set. The replica set creates the pods. And this lineage is interesting. We're going to see it come into play a couple of times. A deployment, and there's a reason why I'm using a fixed width font here, because that's the actual API object, aka code. So the deployment will create a replica set, and we'll talk about the bowels of what that means in a little bit. But the deployment creates a replica set, the replica set creates the pods. Just put a pin in that. We'll talk about that in more detail momentarily. Services, as we've described, add some persistency to this ephemeral world. As things change, I don't want to have to keep up with where they live inside of my cluster. And so it provides a networking abstraction for access to the things that are running in my cluster, right? The pods or the container-based applications. I'll get both IP and DNS, and that IP and DNS will persist for the life cycle of the service that I've defined. So in conjunction of creating a deployment, I also create a service which describes access to that deployment. We'll see like really cool graphics in a minute. Hang tight. We talked about load balancing a bunch, and as things change, the service is automatically updated. Who's ever opened a ticket to the networking team when they deployed a web server that says, I need to add this web server to the load balancer? Anybody done that? That goes away in Kubernetes because of the way that it manages the application state. And services can be scaled by adding and removing, and will be automatically updated. So we no longer have to get in the business of opening tickets with the networking team. Cool. So let's see it in action. So this is a cluster, just a logical representation of the compute resources available to me. A collection of worker nodes, imagine that. But at this level, we're going to focus on workload. So I create this thing called a deployment, which is a description of the application that I want to deploy. That deployment creates a replica set, which then deploys what I told it to do. In this case, I said, hey, you know what? Create 4 pods and run that container, right? Hello world at cloud scale. We'll front end that thing with a service. In this case, it'll be HTTP, and I'll send users to that service. And then the service will load balance the requests equally across all of those pods, right? And that's pretty cool. You can get this in 1 line of code, right, to deploy an app. Or like 87 lines of YAML. We'll get into that. Excuse me. So a deployment is a controller. A replica set has a replica set controller. And so if this happens, if that pod dies, the application stops responding, the node that it was running on Am I back? I'm back. All right. If the pod dies, if the node that it was running on crashes, Kubernetes, the controller manager, is going to be like, you know what, Anthony, you told me to run 4 pods. There's not 4 pods running anymore. Right? So what's going to happen? Kubernetes is going to delete that representation of that object and create a new one for me automatically somewhere else in the cluster if the resources are available to run that. Right? That's pretty cool. You didn't get paged. All right. Let's move forward. So that is what a replica set controller brings to the party, that resiliency in the event that something goes wrong. So now I want to focus on why does a deployment create a replica set? Why doesn't a deployment just create pods for me automatically, right? Because we can do things like this. So this time I create a deployment, and I front end it with a service, and I'm sending users into that service, and it's getting distributed to this replica set of 2, right? I had to reduce it to 2 just because of space. And so let's say my developers come along and they have a snazzy new version of Hello World, version 2.0. I can roll that out into my cluster with 0 downtime, meaning I change the state of the application by changing the YAML that describes what I want to do, by changing some code. We'll look at that in a minute. I give that code to the API server, and this is what it does. It'll create another replica set. That other replica set has the responsibility of running the new version of my application. The previous replica set is currently still up, But what will happen is it will change the state of the application from this replica set to this replica set. And so V2 comes out, it'll start that pod up, it'll shut that pod down, start that pod up, shut that pod down, and while it's terminating and starting up the pods, it's automatically updating the networking to support that, so users will just start going to this application. You just had a 0 downtime rollout. That's pretty fun, right? You notice that the old replica set doesn't get deleted. I can roll back if I need to. So if something went wrong, I can do kubectl, undo deployment, roll back V1, and it'll roll back to V1, right? That's pretty awesome. So you might be thinking, like, how do I do this with regards to rolling out applications and application compatibility? Your apps might not be able to support this type of rollout today, right? Maybe there's a data structure dependency or some sort of session state that just isn't quite compatible between the two. What I would suggest is talk about this model with your developers and engineer towards this. There's ways to engineer towards 0 downtime rollouts to make these kind of things happen. A good friend of mine, Kevin, what's Kevin's last name, Mark? That's Channel Advisor. Yeah, Kevin Fiesel wrote, sorry, lots of Sudafed. Sorry, Kevin. Kevin wrote a session, I saw it 2 years ago at Data Grillin on 0 downtime rollouts. Combining those techniques with these techniques are super valuable. He recorded that and put it on YouTube. So Kevin Fiesel, F-E-A-S-E-L, 0 downtime rollouts on YouTube, and you'll learn lots of tools and techniques that engineer towards this type of rollout. We'll look at, this is what's called a rolling update to get from this state to that state, where you notice it started up pods on this side before it started shutting down pods on that side. There's another type of transition called recreate, where it will shut down all of these pods and start all of those pods in a binary fashion. Right? It's a shutdown start, which gets you between your two versions of your app. And we're gonna look at that when we get into deploying SQL Server a little bit later. So who thinks that's cool? That's cool, right? Yes, sir. Yes, so one of the things that you can do, this is a little bit of an advanced topic, but they gave me a whole hour and a half. So this moves between the state of two applications, but what if I wanted to run this, these two versions potentially concurrently at the same time, or just do an immediate switch and have all the pods standing up? The way that traffic gets sent from the service to the pod is by this thing called labels and selectors. And so you can basically have another deployment, and then you'll change the labels and selectors to transition the workload from A to B, right? And this is, like, again, I'm kind of hand wavy here, but you can do all of that stuff inside of Kubernetes. And I have some resources for that on Pluralsight that I can point you to from Dan Wallin that covers that topic from a developer standpoint. Again, free, I'll give you trial codes if you don't have Pluralsight. So how do I do these things, right? I can do them imperatively, I can do them declaratively, and I can do them in YAML or JSON. Right? So I can just say, you know what, Kubernetes, run this pod, run this deployment imperatively. But we're gonna write code because that's what we do, and we're gonna write it in YAML or JSON. I tried to avoid JSON for as long as I possibly could with working with Kubernetes, but eventually you will have to learn how to use JSON because it's literally how all the information is exchanged inside of Kubernetes. kubectl, the tooling, will just literally convert your YAML into JSON, and that's what's sent into the API server to change state. And when you start debugging things, to get into more advanced topics, you're just gonna have to know it. And unfortunately, I had to learn it too. So, cool. All right, so let's get into some code. So, we talked about the fact that there's an API, and there is an API version. There's an API version that gives you stability on the structure of the object. Right, so a app v1 deployment will always have this structure that I'm going to show you. I'm not going to show you all of the fields that are available, but there are many, many configuration touch points for deployment. This is different than the version of Kubernetes, which is the system version. So how many folks have ever worked on a SQL server before? It's kind of like SQL 2019 can have a compat mode of 110, right? The system version of the data of the software is independent of the actual representation of the object here. And so let's look at a deployment object. We have a kind, that's the thing that I'm gonna deploy. So that's the actual type of object, which is a deployment. A deployment will have metadata to describe something about it. In this case, it's gonna just we're gonna give it a name, hello world. The spec or specification or the technical details of the thing that I wanna build start now. And so every API object, except one, namespaces, has this structure, API version, kind, metadata, and spec. So you always have those four things. Then we'll describe the deployment, like what we want to do. I want to run three things, 3 pods in this deployment. Now, labels and selectors, which we were alluding to a second ago, describe the membership to this particular deployment, right? So imagine this being like a piece of metadata that's attached to the pod such that the deployment can keep track of the pod, meaning it will always look for a label app hello world. A pod will have that label, and that's how it's able to determine that it's a member of its deployment. If it had another application, app hello world 2 or app, super sophisticated application that's not hello world, that would be a different label there because that would be describing the other application. Now, the pod template starts now, which describes what I want to run inside of the container. And so the template also has metadata, so this pod that's going to be created from that container image will have that label, and as long as those match, that's how the deployment is able to keep track of which pods are part of its deployment, right? Yeah. And so here, just a regular old container image. I'm using a Hello World application from Google Container Registry, Hello App, colon 1.0, right? Hello World at cloud scale. And we'll also have to give the container a name. So this is like the bare minimum manifest that describes an individual application. This is the deployment manifest. This is what's called the pod template spec, which is really neat. We're going to learn about later is a super elegant solution to a complex problem using the pod template spec. I save that stuff into a file. I use kubectl to deploy that with the verb apply -f, and it pushes that out. This is really cool for demos, but you're probably going to build things like Azure DevOps and pipelines and GitHub Actions and things like that to actually make this happen. But when you're getting started, this is kind of the way to go with regards to pushing code into a cluster. Cool. So I take that code, I type kubectl apply, and it's going to send that YAML, convert it into JSON, and put it into the API server, and this is what's going to happen. Inside the control plane, kubectl is going to send that stuff to the API server. The API server is going to authenticate me to make sure that I can create the thing that I want to create. So there is a concept of role-based access controls with regards to people and resources. So I push that thing into the API server. The API server stores that immediately in the cluster data store if I have the rights to do so. Right? So it serializes the JSON and puts it into the database. Key value data store. It's on a database. The controller manager is always looking at the cluster data store for new workload. It's like, hey, what do you got? And it realizes that I just put a deployment in there. That deployment created a replica set, which then created 3 pods in the cluster store. Just the representation of those are stored. So the deployment creates that replica set and the 3 pods. So what's going to happen now is the scheduler is going to talk to the cluster data store and be like, yo, you have 3 pods, but they don't have a node associated with them. Just the metadata representation of that inside the cluster data store. That cluster data store then, or the scheduler updates the pod objects of where that workload is going to run in the cluster. The kubelet is always polling the API server looking for work from what's been scheduled in the cluster data store. So kubelet talks to the API server will respond with requests from the cluster data store. And if there's workload for this particular node, what's going to happen is the container runtime is going to pull the container, it's going to start the pod, and then the networking will be modified to send workload into that pod on that node, right? And so this process is important. Seems a little like gory detail right now, but when you're troubleshooting things, kind of understanding this workflow, when something goes wrong, you'll be like, oh, okay, well that part is broken. I can go troubleshoot this thing, right? And we'll see, I'll show you in some debug output in a little bit, where you can kind of see all that process come together. Ooh, right now, okay. Any questions or comments, team? Oh, all right, lots of demos. Sure. So the question is, the concept of a management cluster seems obvious. Could I go over that? What do you mean by a management cluster? You mean something like deploying clusters itself? I don't have a bunch of experience with that, so. Yep. So Docker Desktop, Kubernetes, check that box, you have Kubernetes. I am not running these demos from Docker Desktop. I have a stack of VMs here that I'm running against. So I have a control plane node and 3 worker nodes in my cluster there. Cool. So this code will be all available to you, either on my repo or the conference's repo, so you can reproduce these demos. So we're going to start off with some declarative deployments. No, imperative. See, I messed it up. And I'm going to ask Kubernetes to create a deployment. Say kubectl create deployment. hello world, I'm going to run the hello world image with the tag of 1.0. And so what that's going to do is create my deployment. Okay? I'm also going to run what's called a bear pod. This is often useful for troubleshooting, but I want to highlight a couple of concepts with that. So kubectl run hello world pod image is going to be the same, right? So it happens running an individual pod by itself, which I told you no one gets in the business of running pods individually, but here we are. So if I ask Kubernetes what it's got going on, it has do kubectl get pod, so the verb get will become part of your muscle memory in the near future, and that's going to give me a listing of the pods running in a cluster. You can see the bear pod running here, hello world pod. It's up and running, so 1 of 1 means one container is up, running, and ready, and its status is running. You can see the life cycle or the age on the right, and if there's any restarts. If they restart a container, generally means something's wrong with your application. We also have this thing here, hello world, and then this kind of hash value and a unique identifier there. We're going to focus a little bit on that in a second here. I can also get -o which gives me more output about where the thing landed in the cluster. So I can see the individual pod's IP and the node that it was scheduled to. So it's kind of valuable when looking at where things live. So let's look a little more closely at C1 node 1. So I'm going to SSH into that node because I told you that Kubernetes has one job, right? It starts containers on nodes in the cluster. And since I don't have Docker, I'm using containerd, I have to use this tool called CRI-CTL and talk to the runtime endpoint to extract the information. So on the end there, I have a PS just to get a listing of the pods that are running or the containers. And so there you can see the container running hello app, and then the kubeproxy itself, and another pod called Calico node, which is a network overlay pod that I use. So it has one job, right? The other thing that you're going to find yourself a lot doing is troubleshooting why my things don't start. kubectl logs, and then the individual pod name. There's not a lot of output from this individual pod, but you can see I get an entry that describes what port this application is listening on. So that will become part of your standard troubleshooting technique. Most container-based applications deployed inside of Kubernetes write what's called standard out, and then that's going to be emitted into the container runtime and available to you via kubectl logs. Okay. This is super cool if you have to troubleshoot stuff, especially in remote clusters. kubectl exec gives me the ability to create what's called an interactive terminal into the pod that's running, and then I can launch a process, an arbitrary process. In this case, I'm launching a shell, which means I literally get a shell inside of that container that's running on that pod, wherever that is. And so if this was an AKS or in some remote data center, that's all going to run over HTTPS from kubectl on my laptop to the API server. So tell your security folks about that, and they'll be sad, right? So, yep. But it's a super powerful technique for troubleshooting. You can see the host name, you get the IP address of the pod itself. Looking at that right here. So this is just a Alpine Linux pod that's running a simple hello world application that we now have access to. And so you can see that there. If I do a PS -8, ELF? Yeah. You can see that there's not a lot going on inside the pod because of the isolation of containers. It's just my app, the shell that I just started, and then the command that I just ran. But generally, you'll just see one process running inside of a container. So the deployment that I created a long time ago, right, that deployment created a replica set, and then that replica set created the pod. This thing here is called a pod template hash. So the deployment hello world, the hello world with this pod template hash represents, remember how I told you there's kind of a cool technique that describes like the application itself? That pod template spec is it's a hash of the ASCII text from the word spec down. And so when I change a value in that spec, it's going to change and create a new replica set. So what type of value would I change? Maybe a container tag from 1 to 2 to roll out a new version of my application. So that super simple technique of just taking a hash of part of the deployment is how Kubernetes is able to determine that I have to trip an application rollout. We'll look at that in a few moments. Yeah, and there's my individual pod running. And then the bear pod that we created. Or naked pod, depending on how risque you are. So kubectl describe, again, along with logs, kubectl describe will become part of your muscle memory. You can kubectl describe pretty much any resource. In this case, I'm specifying a deployment and piping it into hello world, and we get the gory details about the pod. We have lots of different values here that represent the current state of the application and potentially the state that have to move forward into, right? So things like, excuse me, our rolling update strategy, which is going to be our rolling update is our update strategy, and then the metrics that define maybe how many pods I'm shutting down and how many pods I'm starting up to support that transition between the two states. And there we see the pod template. That's that thing that is hashed that represents the current state of the application, right? This is literally from the deployment spec itself. Going down to the bottom, events will become also something that you'll become intimately familiar with. Events only have a life cycle of 1 hour, because generally we want those to emit into a log aggregator so that you can watch and consume those things on your own. So if you see that come empty in the future, that's not a bug, that's a feature, right? The primary reason is to reduce load on the API server. So they want you to move that somewhere else. But you can see that the deployment had the job, the deployment controller scaled up the replica set with ending that pod template hash to 1. So that describes the change that it just made. Now if I do the same for the replica set, all the metadata that describes it, you can see the pod template hash now. Here is the value ending in 87B. A label is just metadata about a resource. And so you can use labels to describe a particular resource so that Kubernetes can make informed decisions about what's occurring. If I jump down a little bit further in events, we can see that the replica set then created our pod ending in Z or SWL. And then if I do a describe on, of course, and then there is tab complete, but for some reason it's not working right now. So I'll do that. If I do a describe on the pod, this is going to be where you're going to go. If you have a crashing application or something's going wrong, this is going to be where you're going to land for that. So kubectl describe pod describes the actual container application that you're running. So there we can see the container image. It was started. It's ready, meaning its state is ready, so workload is getting distributed to it. From a load balancer, its restart count is 0. If you see that increment, you might need to troubleshoot something with kubectl logs because your application is not doing the things it's supposed to be doing. At the bottom here is another place where I spent a bunch of time. So the deployment created the replica set, which created the pod. The scheduler assigned the pod to C1 node 1. That's one of the nodes in my cluster. It has the responsibility of pulling the container image. So that's what we see here first. You can see that the image was already present, so that was cached. So all I had to do is create the container and then start the application. As we learned yesterday, this can become a painful place for very large container-based applications. For those of y'all that weren't there yesterday, I deployed a 6 gig container across 3 nodes in a cluster. So that means each node in my cluster had the responsibility of pulling 6 gigabytes of data down to it, right? If you have a node that's 50 or 100 nodes, that gets to be a spicy meatball. And so that takes a lot of time sometimes, and then it also takes time to start up your application. And so that's a place where you can go to troubleshoot those things. Cool. All right. So let's get access into that app. I'm going to expose my deployment imperatively. So this kubectl expose deployment, this line of code will create the service. I'm going to send user workload to port 80, and then the application itself is listening on 8080. Those ports don't have to match, right? So I run this code. Maybe run that code. And I now have a service that I can send traffic to in my cluster. So I'm going to send traffic to this IP here. Grab that, and do a curl, HTTP, bang, bang, and there is hello world at cloud scale. Cool part about this application, hello world, gives me a version, and it also tells me the pod that it's running on. So it gives a good visualization of where the workload's actually running in the cluster when I start hitting the services, right? One of the things I don't like doing is writing YAML, so I can ask Kubernetes for the YAML representation of an existing object, right? And so that's what we're doing here. So kubectl get deployment, whereas a few minutes ago, I would just get this output. I can add an output modifier to give me the actual YAML of the object, right? Then I can use that to maybe build a more complex thing inside of my application. So here we see the things that we looked at when we looked at manifest, API version kind, metadata, and a little bit further down, spec, and some additional metadata that was added by kubectl when it created that deployment. So going down a little bit further inside of the spec, a lot of these are default values with regards to how to roll out more sophisticated applications and control the transition between the two states of a replica set. But there we can see things like the spec and containers, kind of the minimum of what we need to get up and running. Let's go ahead and do this now. So I don't, whoops, kubectl, nope. Get pod, I'm gonna take this pod, And I'm going to delete this pod. So kubectl delete. So I delete that pod. What's Kubernetes going to do? Who said that? Make a new one, right. And it's not the same one. It's the same configuration of the previous one in my application. So if I do a, oops, I have a new pod, right? You can see the pod template hash stayed the same, but the ID on the end here is different. And it was from 21 seconds ago. And hello world pod is still hanging out. So if I delete hello world pod, what's Kubernetes going to do? Nothing, right? It's a bare pod not under the control of a controller of a deployment or a replica set, right? So now I have that, right? Just the one that's left. Cool. So let's start over. One of the cool things about Kubernetes is being able to roll things out really quickly. Another one is to delete things really quickly, right? So you can just get rid of all the stuff that we just created. Now I'm going to switch to creating things declaratively. So I'm going to use the same syntax that I did a few minutes ago, but since I don't like YAML, and I don't want you to kind of learn how to use what's called a generator, you can take this imperative command and combine it with these parameters here, dry run client, output YAML, and what that will do is give you a manifest for the thing that you want to create, right? Which is pretty cool, because now I don't have to write YAML and like curse white space and things like that, right? And so inside of there, it's very basic plumbing for a deployment. I can take that and write that to a file. And I have a file that has all those contents now. And I can take that and send that into the API server to do things. So this is pretty good for just bootstrapping the simplest of applications. So there it creates my deployment. I can also do the same thing for a service. And so if I do the expose that I did a few minutes ago, here you see I get the API YAML representation of a service running on 80 and sending traffic to containers running on port 8080. And I can do the same thing, put that in a file. I have the file that represents all of that, so we double check those things. That's the config, and then I can roll that out. And so the value of this now is I have the actual configuration representation of my app, which I can put in source control. Hopefully people don't change things. And then I can use that to deploy elsewhere or wherever I have the Kubernetes API. So let's make a change. I'm going to change this to 20. Save that out. And what's Kubernetes going to do when I save that out? Nothing. I didn't do anything yet. I just I changed the file. Now it does it because I pushed that config into the API server. So the desired state of the cluster goes from 1 replica to 20. And then all that stuff that I talked about with regards to the deployment controller shifting state, the scheduler doing its thing, figuring out where to run the workload, all of that plumbing has to happen. And behind the scenes, I get 20 pods supporting my application now, right? Which I think is a really powerful concept. I now have 20 copies of my application to support user workload, given that I have enough compute resources to run that, right? It's a very powerful concept. I worked for a long time in e-commerce, and I would spend September and October building lots and lots of web servers for the holiday rush, right? That's not fun. Who's done that? I've done that. Yeah, and so I've had customers that would run on 2 web servers for 10 months of the year and 85 web servers on 2 months of the year. But what if I could just do this, right? Or what if I could respond to load in this particular customer? Marketing didn't communicate with IT and started a campaign, and next thing you know, they were on the Today Show and 8 million people went to the website. What do you think the website did, right? At least if they would have given us like a day or two's notice, we could have actually supported that workload using these techniques. Like it wouldn't respond immediately. Like we still need the compute power to do the things, but we would have had a fighting chance if they'd have given us some time. So we exposed that via service. And I told you earlier, we get this really cool functionality of automatic load balancing without having to go and do any networking stuff, right? So if I run curl across that particular service IP, which is the persistent endpoint, you can see I'm automatically getting load balanced to individual pods. You can see the pod ID changes, right? Which is pretty cool. Again, I didn't have to open a ticket, do nothing, it just works, right? I can edit the deployment in real time. This isn't great, but it's cool if you have to like troubleshoot something. So what this does when I do an edit is it retrieves a representation of the API object from the API server and gives it to me in a local editor, right? My local editor happens to be VI. And generally, the more impressive thing about this demo is that I can exit it without fighting with VI for 20 minutes. But what I'm going to do here is change this from that to that, so replicas from 20 to 30, and that's actually going to send that back into the API server or make the change. So here we can see edit it. Not great, because now I don't have that code that describes that change, right? I made a change to the cluster, but the code that I used to deploy it doesn't have that change. But sometimes you got to do things, right? Cool. And if I do a git deployment now, it's up to 30. And similarly, I could scale imperatively if I need to, just by changing the deployment. So it's kubectl scale, deployment hello world, and replicas equals 40. I now have 40 copies of my application running across all of the pods in my cluster, right? Which I think is so, so cool. And you can see all of those up and running and working, supporting workload. And they'll just be load balanced too, automatically. This ends at 10:45, right? 10:45? Yeah, okay, cool. All right, so let's do some cool stuff. So now I have 40 pods up and running. And I'm going to push a bad deployment out. Okay, something's wrong with this deployment. We're going to troubleshoot it together. So all these are up and running and supporting my workload. Everybody's happy. The developers give me a new version of the app, and they're like, roll this thing out. And so I roll this thing out. And I check the rollout status of that. So kubectl rollout status will block until the rollout finishes or fails, right? I actually shortened the deadline of the failure to 10 seconds because I didn't want to have y'all wait for 10 minutes because it would get really awkward, right? So that should fail after 10 seconds. If it doesn't, I can just break out of that. So I think I'll just break out of that. Let's see. So that didn't return an exit code. I must have just finished. Yeah. So a non-zero exit code means failure. So if you're building tooling around rollouts, this is a way that you can inspect if your rollout actually finished. So now what I'm going to do is a kubectl get pods, and we can see there's some weirdness going on. And so I had 40 pods rolled out. I sent another deployment in to give me the switch between version 1 and version 2 of my application, but something went wrong, right? And so these pods don't say ready. Like these are running and ready from the old replica set. So hello world and the pod template hash ending in 8C7. I rolled out a new version of my app. I got a new hash. So there it ends in 6C5. And these all have image pull, so they're not running, and they're not ready, so they're not getting load balanced to, which is cool, right? Because then it's not affecting my application, but a subset of my apps did have to shut down to support this transition. So I shut down a bunch of pods, tried to set up a bunch of new pods, but these didn't convert to ready, so the deployment stopped, which is pretty cool, because then it protects you, right? And this is with the default settings. You can get very granular about how you want to transition between the two states. So all those configuration points that I glazed over in the deployment spec when we looked at the details of that a few minutes ago, those are all the knobs and buttons that you can tune. And I have a link to the documentation to show you that. So let's look at what happened. I can use rollout history to check the configuration of a rollout. So I had 2 rollouts, the initial one and the second one. So that's the one we started with, that's the one we changed to. This change cause used to be a way to store metadata describing what changed in a deployment that's being deprecated, so I didn't even bother to populate it for this demo. If I look at the deployment itself, let's see. I can see the current state that I'm in. So this annotation here describes the current state of the deployment. So you can see I'm on revision 2. So between here and here, I kind of know where I'm at. I started here on V1. I changed to V2, and I have these 2 rollouts to work with. And when I say rollouts, that's the representation of the configuration for the individual changes to the deployment that I made. So I can ask Kubernetes, hey, you know what? Tell me about that first deployment. And that's what we're doing here on line 242. That first deployment, we rolled out V1, right? Super sophisticated demo of deploying out hello app V1. So this is the pod template. Again, it describes that particular version of my deployment. If I look at V2, I can see that I have this pod template, the image. Well, I have a typo. It's hello app instead of hello app, right? With 2 P's instead of 1 P. So, all right, I'll go back to developers and be like, listen, I need new code, but in the meantime, I can roll back, right? So now it's going to shut down all the new pods and start up pods to bring me back to 40 replicas on the previous version of my application. So now I check my rollout. That should finish in a few minutes. You can see it's transitioning back, so starting up the previous version of the application. Now the exit code from that will be 0. If I do get pods, I'm back to where it was, right? which is kind of cool because now I protected myself from a failure. I roll back and I'm back into the original state. I didn't have to talk to developers to get new code and make a change forward. I literally just went back, right? So pretty fun stuff there. Any questions or comments about deployments and rollouts and things like that? And a successful rollout, what would have happened? I would have just had V2 of my app, right? And it would just transition between the two states. Cool. Any questions before I delete all of that? What's up? Yeah, so generally, so the question is, where does the image come from, basically, right? If I go look at the deployment, in this case, the image is coming from a container registry, the Google Container Registry, or GCR, right? Developers will take, the workflow is developer builds the image, pushes it into a container registry, and then Kubernetes has to have the ability to read from the container registry. And so that's what's happening right there. So, you know, I make a new image, push, it sits there until I describe that I want to pull it down. So watch my session yesterday. So, good question though. Yeah, that was tough yesterday with the video. Cool. All right, so that is stateless applications. So we did a bunch of stuff in there, like a lot. And all of that you can do in Docker Desktop, and I strongly encourage you to do, and I'll give you all of the code. So we deployed an image imperatively using kubectl. Let's go kubectl create deployment, right? Kind of fun to make some things. We accessed that service in a cluster. We saw how load balancing works. We made a change, we broke it, and then we had to look at some advanced deployment operations to roll back, right? Super fun. Oh, wait. Yeah, cool. Okay, so we have another hour. So that's stateless applications. Stateless apps work really well. Advanced topics regards how to roll out and things like that. So I encourage you to dig a little deeper if you want to get into controlling rollouts and things like that. But now we're going to shift gears towards stateful applications and my favorite SQL Server, right? So we talked about this in the beginning. A pod goes back to its initial state each time it's deployed. I don't bring state along with a pod. If it dies, it goes away, then I'm going to create a new one, right? So that leaves me with a couple of challenges that I have to solve when I'm deploying stateful applications. And this applies to any stateful application. Where do I store the actual data, right? If I create a database, where's that going to live inside of my cluster? And then what about configuring it? Because if I'm pulling a container image, how do I configure that container to do the things that I want to do? Because generally things like SQL Server have pretty complex system configurations, right? When I actually want to describe how SQL Server itself works. So how do I do these types of things in a platform that's really not mesh, I shouldn't say that, but doesn't have those constructs out of the box, right? If you go on Twitter and talk about databases and SQL Server and on Kubernetes, people have feelings, right? Yeah. A really cool job now where I get to work at a storage company and I get to work with really big customers on really big SQL servers, and you can have really big workloads in VMware and be totally fine. You just have to like do the thinking, right, and engineer it properly. That's usually the hard part. Okay, cool. So let's look at this concept of decoupling data and computation. This is a super powerful concept, I think, with regards to how data lives inside of a data center. Right, so we saw this paradigm before about how I deploy an application inside of Kubernetes. I'm going to have that same technique. I'm going to apply that to a stateful application like SQL Server. And so I'll create a deployment that creates a replica set that runs me one SQL Server, right, on whatever version of SQL that I want. I'll have some storage that's going to live somewhere inside of my data center. It doesn't have to be part physically of the cluster. That could be an iSCSI array, that could be an Azure Virtual Disk, it could be a Fiber Channel array. Or if you're into products like VMware has a whole management solution for Kubernetes, like Tanzu will actually automatically allocate a VMDK and attach it to your container for you. So you get storage from your data center, but not necessarily from your cluster, but we have to write code to consume it from our data center. And that's where things get a little sticky. I kind of alluded to that. It's kind of tough, and there's reasons for that. So the deployment creates a replica set. The replica set starts my container. I attach storage, right? I then create a load balancer to send traffic to that SQL server, right? All right, so if that SQL server crashes, what's Kubernetes going to do? Bang, right? You just have a failover cluster now, right? So we're going to get failover cluster-like functionality out of Kubernetes for free just by writing code that says run this container for me all the time and attach some storage to it. The storage will be external, so it'll just be attached. SQL Server will start back up and be like, yay, databases, right? And so now I have access to my apps again. And this is why I don't understand why folks don't want to run stateful applications inside of Kubernetes, because I get this type of functionality effectively for free, right? No offense to the DBAs in the party, but I don't have to have a skilled DBA now to run an FCI, right? I can have a Kubernetes platform engineer that runs the whole platform. And I can then just deploy stateful applications inside of there, right? I'm a DBA, I get it, so. All right, so a new version of SQL Server comes out, cumulative update, something like that. I change the code that describes the deployment. Kubernetes will start a new replica set. We use a different update mechanism as we did before. Before we used rolling update, we'll use recreate now, which means this will shut down, this will start, storage will move, databases are attached, go, right? And I got that in one line of code to patch. If you were doing that on Windows, you'd be arguing with your patch admins right now to get the patches rolled out on a Friday, right? We still have the representation of the previous version, so if something went wrong, maybe there was a bug in SQL Server, it never happens, we can roll back, right? And that becomes a very easy operation. There are some nuances around how fast this transition occurs. If you want to get geeky about that, let's talk afterwards if you really are considering this. But if you look up DBA from the cold, he has a whole blog post about making that transition faster, which is important for RPOs, right? But basic functionality is what we're focusing on today, core functionality to be sophisticated. So storage. So we learned about deployment objects, we learned about service objects, pods, and things like that. But I need to be able to represent storage on my cluster to consume it, right? And so I have an object called a persistent volume, which is going to be administratively defined storage. So you're going to work with somebody in your data center based on the type of storage that you have to figure out what the code looks like for a persistent volume, right? So if you have, I work for a storage company. I don't want to use that as an example yet. Let's say you're in the cloud, or any type of, I can say this accurately. You're going to work with your administrator to define that, and your vendor is going to define what that code actually looks like. And so you're going to consume storage in many different ways. It could be ISCSI, NFS, Fiber Channel, Azure Disk, EBS, whatever it is. Now, from a config standpoint, if I have code that's very sticky to my data center, that's, it has very specific configuration about the storage in my data center, what's that going to do to the concepts that we talked about earlier, where I can run Kubernetes wherever I have Kubernetes, right? I have this API, I can write code against the API. I should be able to just pick this workload up and move it over there, as long as I have Kubernetes, right? Except that, because it's very specific to your configuration. And so Kubernetes did is they added a level of abstraction called a persistent volume claim, where the claim allows you to describe the type of storage that you want, right, in your application. And you're going to have two different objects defined that consume storage, which means if I have to touch code, I only have to touch it in one place. I touch it there inside the PV, rather than having to change my deployment, which is just describing my application. And we'll look at some examples of this in a minute. The claim is what I'll have in my app tier, in my deployment, and then it says, you know what, give me some storage, Kubernetes, and Kubernetes will go and find a persistent volume that matches the storage characteristics that you want. And the idea, as I indicated earlier, is it's trying to break that very data center specific code out from your app code so that I can share this with you and say, you know what, you used to have to write your own PV to make this work, right? The cloud solves this problem with what's called dynamic provisioning, which works really, really well. Ooh, that's hot. Thank you, Mark. So this is a PV, API version kind metadata spec, right? Give it a name, and the PV describes in very gory detail and very specific detail to my configuration, right? And so that is the persistent volume. Inside the spec, we describe a capacity, an access mode, and a type. This type this is where it gets specific to your data center. Where do I get this information? Documentation, right? So you have to go read the docs for your vendor to provide that. So capacity is capacity. Access mode, read write once, means one node can attach to that volume, right? Read write many means more than one, and read only is another option there. A PVC, or persistent volume claim, looks like this, and so this would be part of my app code. You can see it's a little less specific than this in that it describes an access mode and a size. If I create a persistent volume claim that looks like that, it'll go and try to match on capacity and access mode and bind those two things together, and that's how I get the storage allocated on my cluster, right? It's as scary as it sounds, trust me. It's not great, yeah. Yeah, so hold on, let me see if I talk about it. I don't talk about dynamic provisioning, but I have a amount of time. So this is what's called static provisioning, right? Static provisioning means I have to write this thing, and then I have that thing, and then we're going to combine it all together in a minute, so hopefully that'll color into detail. But most cloud providers are doing what are called dynamic provisioning, such that you just write a PVC, and it builds this dynamically for you and allocates that under the hood from the cloud, which makes sense because I can do those types of things in the cloud to get automatic consumption of resources. So if I, in Azure, say, you know what, give me a PVC of type locally redundant standard SSD, and it'll just provision an Azure disk, and I'll attach it to my node, and I can consume that storage. That's where you want to go. But I like to start here because I want people to understand that this is what's really occurring under the hood. This is getting dynamically generated for you in the cloud or in like VMware Tanzu and all the managed solutions. But the PVC, if you want to build this in a lab, I don't have a dynamic provisioner or some fancy flash array underneath my laptop, right? And so I want to go through that in here. So let's kind of bring that all together. So when I'm deploying an application like SQL Server, I have to define a storage tier, right? Just define a storage tier, and where I'm going to store my data. And so there's a thing called an instance directory inside of SQL Server, which stores all of the stuff about your application. So the things that really describe the current state of my app. And that's going to be written into a persistent volume. I'm going to attach that volume to a specific location that matters to my application. So in this case, it's going to be var opt MSSQL. So SQL Server will start up, and it'll put things in this location. There'll be a persistent volume attached to that location, and it'll write to the actual volume itself. And we're going to see that in a little bit. The user database default directory is underneath there. So if I'm just creating databases, they'll be created on that persistent volume that I attached to that pod. Oops, sorry, I got to jump ahead a little bit there. And so with that, now I have data that lives in wherever that persistent volume is, right? In my case, it's going to be NFS. If you did this in Azure, it would be on an Azure disk. And I have a pod that can run anywhere on my cluster. So if I attach that pod to that storage, then I have access to that data, right? So with regards to that's state. With regards to configuration, we can inject configuration into any container-based application with environment variables, kind of like a standard way to inject config to have it decoupled from the actual runtime. So I can describe environment variables in my deployment manifest that say, you know what, configure these things. My app starts up, reads the environment variables, and configures those things, right? So specific to SQL Server, the very first time it starts up, it's going to read environment variables and set some configuration. You need 2 by default to run a SQL Server, except EULA because of Microsoft, and an SA password, right? After yesterday, I'm probably not going to be an MVP anymore. Okay. All right, so that SA password, one of the things that you don't want to do is write passwords in a deployment manifest, right? That's a bad thing, because then if I give that to you, that's bad, right? So we can decouple that and store that as a secret inside of the cluster, or even go further and put it into a secret store that gets read at runtime. And so since that pod goes back to that initial state every time, when I start the pod back up, it can read the environment variables the second time. It starts up, it looks at the storage in var opt MSSQL, and it sees it has data, and then it just picks up where it left off. Right? So now I literally have broken these things into the configuration state and how I get those configured inside of my apps. Who's used SQL Server Configuration Manager to configure a SQL Server? The MMC GUI. So lots of stuff is in there, like what ports I'm listening on, what TLS certificates I'm running, any additional services that need to get run. But there's no MMC in a container to run that. So anything that was surfaced in Configuration Manager is surfaced as an environment variable, and so they're all listed here at that URL there, sir. All right, so the question is, do we have to have SA? I don't know. But on deployment, you would create a new sysadmin, a person in the sysadmin fixed server role, and disable that. It's going to be there by default, but you can quickly change that if you needed to. Yeah. A little bit of an advanced topic is a thing called an init container. An init container can do things before your real container starts, and I wonder if that would be a way to solve that problem. So, cool. Yeah, so our configuration is defined in the manifest. Our state is in our persistent volume. And when SQL Server starts up the very, very first time, this is probably going to where you were thinking about, if there's nothing in var opt MSSQL, what's going to happen is it's going to copy the default databases into that target location. And they're going to have some sort of config, and this is why master is going to be disabled, because they're getting copied from this thing called a single file package, which is part of the container itself. And so once that's laid out, and I've configured that thing. So I've started up the pod the very first time, I've disabled SA, and I put in a new sysadmin. The second time I start, SQL Server is going to go and look and be like, oh, I have a master database, and use that config that's in the master database. Yeah, you can do AD auth in Kubernetes. There's a blog post about that from Microsoft. That took a while to get to, though. Yeah, and if you had created user databases during this first execution, the representation of that is in master, which means if those user databases are available if those user databases are available at the file system level when SQL Server starts up, master's going to be like, you know what, there's a database and attached to it. And then you have really decoupled the state of your deployment from the actual runtime. Yeah, so database is already there, master's read, so any instance level config will be persisted there, and then if user databases are there, they'll be bought online. So, cool. So let's get into a more sophisticated deployment manifest, and so I think this will probably answer your question, Justin, about what that looks like in code, bring it all together. So API version kind metadata spec, this one's gonna be a deployment replica of one, which is gonna hopefully give me the guarantee of having one SQL Server on all the time. The default strategy or update strategy is a rolling update, which we saw a little bit ago. Now I'm gonna change that to recreate because I want SQL Server to shut down first before I start up the other one, right? Because if I started up the other one first using rolling update, it's gonna crash because it can't get an exclusive lock on the files. It'll sort itself out, but that's not the most graceful way to roll out an application. So inside the deployment spec, we saw a little bit ago that when I use kubectl exec to go inside the pod and I typed host name, I got the host name of the pod, right? That's how it is by default. The host name inside the operating system of the running container will be whatever the pod's name is. If that's a SQL server and that's changing all the time, that could be bad news for things like transaction replication or your monitoring platforms. And so we have the ability to inject a static host name, in this case SQL 01. And so when SQL Server starts up, it'll set that host name, or when a pod starts up, it'll set that host name. SQL Server starts up, reads that host name, and sets that in its metadata inside the instance. So if the pod goes away and comes back, SQL Server still thinks it's SQL 01, even though the pod template or the pod ID is going to change, right? So monitoring systems get cranky about that, and transactional replication does too. The first couple iterations of SQL Server containers ran SQL Server as root. Dun, dun, dun. Right? Bad news. Again, Andrew Prusky, DBA from Nicole, has a fantastic blog post about this, where if you run a container-based application as root, or even a regular Docker container as root, Linux works on the concept of user IDs. And so if I'm executing as user ID 0, which is root inside of the container, and I attach a volume to that, which I can attach an arbitrary file system location from the base OS into a container, well, I'm now running a process as root. I go touch a file as root. That's the protection mechanism on files. So I could start a container and arbitrarily change the configuration of the base operating system because it's just files in Linux, right? That's super bad news. And so we don't want to run containers at all as root. And so this is a way to tell SQL Server that's going to run as the user ID 10,001. And we'll look at that in more detail when we get into the containers itself, or when I start deploying SQL Server. So it's going to run as user ID 10,001, a non-zero user ID, so non-privileged user. So now, next thing I have to do is define a container. So that's the image that I'm going to run. So 2019 CU13 on Ubuntu 20. The container itself is going to listen on 1433, not the service. And then we're going to define some environment variables. So I gave it a key, which is the environment variable name itself, and then a value. This one's a static value of y, which is the default to accept the EULA. Then the SA password is going to be read from the secret key store. It's going to look for a key named MSSQL, or a secret named MSSQL with a key of SA password, and then it's going to read that value into an environment variable, and then SQL Server read that on start and set that up. The volumes are going to look like this. I'm going to mount the volume name MSSQLDB. That is going to be at that location. So conceptually, the volume mount is like I'm going to plug the drive in at that file system location. So very much so like a mount point in the Windows universe. That storage is going to come from the volumes that we created a few minutes ago. So MSSQLDB, the PVC name SQL data. So that lineage of volume plus PVC plus PV is how you walk down the storage stack so you can see where that stuff actually lives, right? So if that wasn't hard enough, we're going to do advanced disk topologies now. Because what DBA runs all of their disks on one single drive, right? Yeah, I know you do. Your workload's so unique, Mark. Yeah. So your code is going to get a little hairy, but you're going to basically create PVs and PVCs for each one of the disks that you need to consume. And then what you'll wind up getting towards when you're building this in an enterprise data center is you'll have classes of storage. I'll have a platinum, gold, bronze, silver, or whatever I want to call it. And you'll get to the point where you're like, you know what? All right, well, this tier 1 database, its database volumes and transaction log come from platinum, which would be sub-millisecond, whatever class of storage, is available to me in my data center. And it may be, backups are going to go to a higher latency disk that's on the bronze tier, right? And so you can kind of get, you got to write code to consume those resources, but your data center has to kind of support that dynamic allocation. And you get that in the cloud, and you get that from some managed providers like Tanzu and things like that. So yeah, we'll define our storage tier. We'll put some configuration in a SQL Server to tell it to create new databases in those default locations. Kind of a normal DBA setting that says, create new databases on these folders, right? And so in our case, we're going to set that to /data and /log in our deployment, and then new user databases will be created in there. So maybe this is, on silver, and that's on platinum, because that's going to get me 0.3 milliseconds into the transaction log. Right? I can break things out in that way. Who said that? All right. Let me finish this slide, and it's going to get real nerdy now. All right. So on pod creation, the PVCs will be attached, and the master will be written into wherever you define it to go to, and stand everything up. All right. We'll look at that code in a few minutes. There's no swap in Kubernetes. 0. And it's actually quite an important thing. If I have a cluster of resources, and one of those applications gets bad and starts allocating too much memory, and that underlying OS starts swapping, what's going to happen to the rest of the workload on that node? It's going to tank, right? And so rather than bring down the whole node, there's no concept of virtual memory from a swapping standpoint in Linux Kubernetes nodes. And so it'll kill the thing that's consuming too much memory to protect the rest of the workload on that node, right? And so when you're deploying applications, you're going to just engineer towards this. And this is something that I talked a bunch about with the Microsoft product team for SQL Server, in that SQL Server can consume lots of memory and do potentially really bad things in swapping and things like that. And it's as heavy-handed as it sounds. It's the best way to protect the overall health of the system. On Windows nodes, there's swap, which can bring you to some bad things. Oh, resource management. Let's get on to the future. So we can define resource management at the pod and namespace level. I didn't quite define what a namespace is yet, but a namespace is a way for Kubernetes to subdivide an allocation, subdivide the resources in a cluster. So I can create a namespace for application 1, and so application 1 can only start up 50 pods and consume 100 gigs of RAM. I can put a boundary around that, right, across the whole physical cluster. Or I can do it at the pod level, which when I'm deploying SQL Server is more generally the case. I can put constraints around CPU and memory. So I can say, you know what, you can only consume this much CPU, and you can only consume this much memory. On our system for SQL Server, that's extremely important, because if I have more than one SQL Server running on a node, and both of those SQL servers start up on a node, they will both see how much memory each other has in that underlying node. If it's 32 gigs, they're both going to potentially allocate 32 gigs of RAM. Now, in a Windows instance, there's a concept of external memory pressure, and they can kind of balance each other out. On Linux, there's not. And so it's up to you to really control how much memory is being allocated. So if I have an application that I want to deploy, whether it's SQL Server or not, I always encourage customers to define what are called limits and requests. And so a request is a guarantee. So I say this SQL Server needs 16 gigs to start, right? And it's going to go across all of the nodes in a cluster and find a node that has 16 gigs available for that SQL Server, or that pod, whatever it is, to start. A limit is an upper boundary in that if I exceed that, I'm a candidate to be killed, right? And so that's how you protect against swapping. Specific to SQL Server, you'll combine both the limit with max server memory to make sure that you stay below, right? So really, it's understanding your application and then setting the boundary for your application such that if you exceed that boundary, something bad's going to happen to protect the overall health of the system and then kill that pod, right? So you always want to deploy with limits and requests. There's no limits by default, which can lead to some really interesting scenarios with regards to consumption of memory. Because if I start up any application, not just SQL Server, it's going to see, oh, I have all the memory. Okay, let me go do some things, right? And so yeah, you should absolutely set it. And so with regards to how to set that inside of a deployment manifest in the container section, so it's a per container setting, define resources, requests, CPU, memory, limit, and then similarly for limits. So this particular SQL Server would have to find a node that has 1 gig of memory available. If it doesn't, it just won't start, right? And that's good because I'm not going to put my cluster in a bad position of starting this thing up and potentially allocating that memory and causing bad things to happen from a resource over allocation standpoint. Similarly, from a limit, if my application goes out of control and starts doing bad things, I can kill it, right? Just again to protect the overall health of the system. Server instance settings still apply. They'll be stored inside of master, so in the end, your app still matters, right? You have to configure your application, but these are just kind of guidelines or guardrails so you don't destroy the rest of your cluster, the performance of the stability of the rest of your cluster. Now backups, this is kind of a DBA-specific topic, but really what the idea here is I can just allocate storage to do stuff inside of my cluster. In this case, I can just add additional storage to my SQL Server pod to run another type of workload into it. In this case, it's going to be backups. And so those could live anywhere, Azure Disk, Azure File, anywhere inside of my data center, and I can consume those resources. Backup to URL is a pretty cool feature, and you can drive those backups with all of the normal DBA techniques that you might have had. So things like all the Halligan scripts, maintenance plans, or the awesomeness of DBA tools. Who's used DBA tools? About 6 of y'all. I don't even know T-SQL anymore. Let's be serious, because I do everything, and I jokingly said I don't know PowerShell yesterday, but I literally do everything in DBA tools when it comes to maintaining SQL servers now. So, cool. All right. Got half an hour for demos. This is going to be fun. Any questions or comments, team? What's up?
In front of your SQL instance, do you still have a load balancer?
Yes, good question. I jumped over that. Let me bring that slide back up. So, in this case here, bang, bang, bang. So this deployment, let's get into some gory detail. So this will be a persistent IP address associated with that. So, 1.2.3.4 on port 1433 or whatever port I decided to be. This will route that traffic to this individual pod. The individual pod will have an IP associated with it. So in the previous example with all those hello world pods, every single pod had its own unique IP address. And I sent traffic to the service, and the service load balanced across all of those. In this scenario, this pod dies and comes back, there's no guarantee that it's going to have the same IP, right? And so what will happen is when this pod dies, and I said when it comes back, it doesn't come back. A new one is created in its place with the same configuration. That'll update the service, and then the service will send the traffic to wherever that pod landed in the cluster, right? Exactly. Yeah, just to add the persistency on the front end so you can send your apps to it. I mean, you get that, effectively you get that with an FCI, because an FCI, you have a VIP that you send your traffic to, and the VIP floats across the nodes in a cluster, right? So the paradigm kind of applies there too. So the question is, where are the PVs actually defined? The PV is a API representation of a physical thing, right? Or a virtual thing in the sense of like an Azure disk, right? But it's a physical resource available to me to consume in my cluster. And so let's look at that right now. So what I'm going to do first is I'm going to set an environment variable, and then I'm going to create a secret in the cluster. And the reason why I'm setting it as an environment variable is because I'm going to reuse it over and over again. So I'm going to create the secret, which is going to have my SA password, and I'm going to create my storage tier first. And so I have PV and PVCs broken out into 2 different files. And so let's look at both of those. So the PV is the application-specific representation of the storage in my lab here. And I have a simple Linux box that's running NFS, right? And so PV NFS data. So this is where the user database data is going to go, and it's going to live at this type of storage at that location. So this stuff up top generally isn't going to change. This is going to be specific to your provider. So that could be iSCSI. That could be Azure Disk, EBS, NetApp, Pure Storage. Like they all have different types of integrations at that point. And then I have the other storage available. So I created 3 in this case. So one for logs and one for system databases. Right? So I have 3 PVs being created. And then I have 3 PVCs being created. No, we're going to get into that. Yeah, right. So the PVCs are the description of the storage that I want to consume from the cluster. And so when I create these objects, the PVs and the PVCs, what happens behind the scenes is I get this. I get PV. I have all the storage created, and right now they're bound. And the only reason why they're bound is because I created the PVCs. If I did these one without the other, what would have happened it would have created the PVs, and it would be unbound, meaning there's no claim on that yet, right? So now there's a claim, and an application is going to come along and attach to the claim in order to get access to the individual disk, and that's what I'm going to do right here. So I'm going to roll that out. Let's look at advanced disk. So we went through this part in the presentation, so I'm going to have a deployment of replica 1. Talked about security context, the container itself, so this is kind of the more complete version of that. Now, what I didn't cover is because in the presentation part was the actual disk layout for the more advanced disk configuration. So I'm saying, you know what, set these 2 variables to /data/log. So when I create a new database, it'll land in the appropriate location. And here's the more advanced disk layout. So system is going to go at this location, var opt MSSQL. Data is going to go /data and /log. And then those volume mounts will be attached to these volumes. And so you can see kind of the lineage of that in that the volume mount for var opt MSSQL is named system. It's going to read this volume. And this volume is going to read that persistent volume claim. That persistent volume claim is going to read the PV that we just created a few minutes ago. It's hairy, I know. I'm so sorry. Yeah, basically. And then here's the service that represents where we're going to send traffic to. And so this time, I'm using a different port for the load balancer, but SQL Server is always going to listen on 1433 inside the container. So I now have a fully functioning and configured SQL Server that took just a few seconds to get up and running, right? Which is totally cool, I think. I told you have to use JSON eventually, so here you go, there's some JSON. So I'm going to just ask, since this IP can change, so I have this code here so that you can just extract that and then store it in an environment variable so we can use it to address the SQL Server IP import. So I'll ask SQL Server, hey, what version are you running? So that is an up and running, functioning SQL Server. I want to create a database using that same technique. So I'm just using SQL CMD to blast tsql at the instance. So I created a database, and now I'm going to ask where SQL Server thinks that stuff lives. SQL Server thinks it lives here at var opt MSSQL, and this is the key to understanding the physical topology of where things live. SQL Server thinks it's at this location, and it's up to the container runtime to manage that translation because it doesn't actually live there, right? It's up to the kubelet to attach the storage. So the kubelet's responsibility is to literally mount T, NFS attached to that thing. Or if it was an Azure disk or some sort of other type of disk topology, the kubelet has the responsibility of getting that storage into the individual node that pod is scheduled on, and then the container runtime makes it think that it lives at that location. And so if I go and I look at my NFS server, so I'm just using SSH to blast a command at my storage server, and so I'm just getting the directory listing at that location. So this is where my stuff physically lives in my laptop at that NFS server. And so that abstraction, although be it quite complicated, gives me the ability to decouple these things, right? And so I'm using NFS as my storage tier. This could be any other type of storage, and what would happen is SQL Server writes the var opt MSSQL. The kubelet attached the storage, but the bits and the bytes actually get written out to where I tell it to under the hood, right? Cool. And you can see these are all created just a few seconds ago because it was the very first time SQL Server started up. And if I look at data and log, you can see that the MDF and LDF are split across that. So I'm getting that, good, almost production-ready storage subsystem. So shutdown with no wait is a way to crash SQL servers. Anyone ever used this before? Yeah? So it's analogous to pulling the plug, kill -9 on SQL Server itself. So it crashed, and that yields a non-zero exit code. And that's really the key to helping Kubernetes understand what happened inside the application. We talked about like probes and things like that, but there's another level of protection inside the pod itself. If my pod crashed and my application crashed and it yielded a non-zero exit code, Kubernetes by default would just restart that container inside that pod. And we don't have to go through the harder transition of scheduling that pod somewhere else in the cluster and maybe potentially having to move storage. So it'll restart that container inside of the existing pod structure. And so that's what we see here is we don't get rescheduled, but what we do see is it compresses error messages. So we see X2 over the last 4 minutes. Well, 4 minutes ago we created it, and then within the last few minutes or 18 seconds ago, these 3 entries happened again. So the initial deployment was pull, create, start. And when I said SQL Server crash, instead of scheduling it somewhere else, it's like, you know what, I already have the container, let's just restart it, right? So it's a very powerful recovery technique. But you're gonna wanna know when that happens, and so you can go up here, and one of the metrics that's tracked is restart count. Last state was terminated because it yielded a non-zero exit code, right? And so any application is generally gonna yield a non-zero exit code in failure, giving Kubernetes enough information to just restart that container if it needs to.
What kind of probe does it use for this? Yesterday in the web app demonstration, you had it look for a URL.
Mm-hmm.
What does it do for SQL?
So that, what it's monitoring right now is if the process goes away and literally shuts down, and then it's gonna read the exit code of the shutdown process. And if it's non-zero, it'll just restart. Right? So there's no probe in that sense. But we could add probes if we wanted to. Yeah, okay, cool. All right, so let's do this now. So if I delete this pod, what's Kubernetes gonna do? Right, see, and I still have my job after that, right? Because the state of my applications has nothing to do with the pod, right, nor its configuration. And so if I do a get pods now, it's a completely new pod, right? I have a new ID, same pod template hash because the config didn't change, but I have a new ID here at the end. And if I do a kubectl all the log entries from the previous pod are gone because this is a new pod, right? So that's why log aggregators are a big deal. And the other important part is I still have all of my data now. I deleted the pod, created a completely new pod, and it just attached to the databases and go, right? Because we've decoupled those things. All right, how much do I got left? I think we're good. All right. So now I'm going to put some limits on it. And so in this config here, I'm not going to show you. So one of the things that folks need to understand is when I deploy this application and I change a configuration, it will shut down the pod and deploy another one, right? And so that caused SQL Server, when I did this, I changed the config and it caused it to shut down and start up a new one. If I do kubectl get pods now, my pod is pending, and it can't start, and it's 0 of 1. And I'm wondering why. Like, what did I do, right? I mean, I know what I did, but so again, my favorite command, kubectl describe. If something is wrong, this is where you go, right? It's kubectl describe pods, and it's going to tell you it failed scheduling, right? The default scheduler couldn't find a node in the cluster that had a sufficient amount of memory because I put a request on that deployment. And so let's look at that request. I asked Kubernetes for 8 gigs of RAM. Every node in my cluster has 2. So it literally couldn't find a place to run that in my cluster. So it protects the overall health of the platform, and puts that pod in pending rather than scheduling that pod. So the second manifest requests only 1 gig of RAM, and then boom, my pod comes back, and then my SQL Server's back up and running, right? So you can see. And so even though it does have to shut down and start, it's pretty fast, right? So your buffer pool is gone. You have to take that into account. If you had a long-running transaction, you have to take that into account. If it actually crashed and there was a crash recovery that had to undo a transaction, so all the normal DBA stuff you have to take into account on moving between the two. Accelerated data recovery helps attack that that crash recovery problem, because then you get constant time recovery on the time the instance starts up. So I do encourage folks, if you're in 2019 or better, to look at using ADR to solve that problem. Okay, so let's go ahead and I want to add a disk. And so it changed. So you can see I created 2 new PVs. I'm not going to go through the code to add a PV and a PVC to add a backup disk, and I configured the deployment to attach that disk. And I'm going to use some PowerShell. Go figure, right? Only because I love DBA tools. I want to make sure that folks I'm encouraging folks to use this. So since I switched environments from Bash to PowerShell, I have to just reinitialize some variables. So all I'm doing here is creating a credential, getting the service IP, and setting the port. And I just want to highlight really that it's just SQL Server. So like DBA tools didn't have to do anything special to make these commandlets work. It just works, right? And so I can connect to the instance just to verify that the plumbing's up and running before I go and do something. And so I'm just going to run backup DBA database to back up my databases from my SQL Server into a network share. And I can do that with 1 line of code, and we got that cool progress bar that we learned about in the keynote, right? Yeah, but sorry, I have to leave back. Go back to about what, DBA tools? Oh, okay. That's it. We can talk about that afterwards, but that's a huge thing. Yeah, yeah. I mean, and and even talking with a lot of folks and customers about, I don't expect anyone to rip out their Windows boxes and drop this in. But if your developers and architects are shifting your entire platform towards Kubernetes, you don't have to, but and then it kind of goes back to what I talked about in the beginning, having a single group of platform engineers that can maintain the whole platform, right? Not having VMware pros or physical server pros. I can have Kubernetes pros that maintain the whole state of an application deployed in one environment, right? And it depends on the org and the skills in the org and all of those fun things. So let's update SQL Server. I'm going to change from CU13 to CU14, just like that. I certainly could have gone and changed the YAML manifest to the kubectl apply, but in this case, I just went ahead and changed it imperatively at the command line by setting the image to CU14. And so that's going to trip a rollout, leveraging the rollout strategy that we described. So it's going to shut down the first SQL Server before it starts up the new one. And so when I look at what's occurred is each time I changed the configuration of SQL Server, I got a new replica set representing the state of that particular change. And so you can see 12 minutes ago, 4 minutes ago, 2 minutes ago, as I went through the various iterations of changing the limits, correcting the limits, attaching the backup devices, and now upgrading SQL Server, right? And you can see each time it went from 1 to 0, so scaled it up to start, scaled it down before it started the new one, right? And that's what happened for each one of those changes. And I also have all of the replica sets available to me to work with. They're in alphabetical order. And so, or at least I think ASCII sort order. Yeah, it's ASCII sort order. And so we can see that's the current replica set because it's actually up and running. But I could roll back to any one of those arbitrarily if I needed to. So yeah, only one at a time. Now when you do move between CUs, SQL Server does stuff, and so that transition could take a minute or two. Yeah, exactly. So and there is my pod. Again, if you were having to roll out a patch to SQL Server, that doesn't take that long, right? So that's a very powerful technique to roll that all out. If you keep 10 by default. So they will stay until you hit 10, and they'll start pruning them off. And that's a configurable attribute in the deployment spec itself. What am I doing? Copy. So, as I indicated earlier, most applications will write the standard out. Standard out is aggregated by kubectl logs, and so I can just ask for the logs of the application. And so here we can see it's literally just the SQL Server error log, right? And so if you're working with developers and building applications, you want to encourage them to write and emit all of their logs to standard out, and then the infrastructure will aggregate those things. So you don't want them to have to necessarily emit into a logging platform. I do have customers that build integrations into things like New Relic and things like that for performance metrics. Those things still apply. So, cool. All right. So with as easy as it is to roll out, I can also destroy the whole platform that fast, right? However, that data is still there, right? If I go and log in and SSH into that box, that data is still going to be there, and so that's not going to get destroyed. One thing I didn't quite cover, and I have a few minutes to get nerdy about it, is this. Retain and reclaim policy. So let's talk about reclaim policy real fast. So if you're in a cloud, and I destroy a SQL Server instance that I just created, and do I want that disk to stay around after I delete my SQL Server? Maybe, maybe not. Maybe I do because I want to keep it around because I like staying employed. Or maybe I don't because I don't want to pay for it anymore. So that's where reclaim policy comes in. So retain will keep that resource around until you go administratively delete it. Reclaim, which is the other setting, if you were provisioning storage from an underlying storage provider and I said reclaim, when I delete the PVC, it'll automatically delete the actual storage, and then the bits and the bytes on the thing, that storage media will actually go away, right? So. Yeah, the generate resume. I also do have a minute to geek out. DR isn't a Kubernetes thing. DR is an application thing. So you still need to protect your data with inter-site replication of backups, availability groups, whatever it is that you want to protect your data with. Kubernetes isn't going to provide DR for you in that sense. If I want another Kubernetes cluster, well, I'll just build another one somewhere else. And since it's just an API, I can deploy my app over there either at runtime or ahead of time. All right, sir? Yep. So there is, so this thing. There's not a vault. This thing is, when I did this, what that will do is it'll base64 encode that string and store that in etcd in an unencrypted way, right? Because it's just a base64, yeah. And there is an ability to inject encryption into that, but I see most people doing is you run either in a container or a sidecar container that will go and pull a key from an actual key store. That's not this. This is like super basic stuff. With regards to just the functionality of storing the secret somewhere. But I wouldn't consider it protected. And similarly, like that etcd thing, the cluster data store, that gets backed up, you need to make sure to understand that your secrets are in there. If you're storing them in here, if that gets compromised, bad things happen. But you can encrypt that if you need to, but most folks will use an external key provider. So, cool. I don't think I've ever finished early before, like literally ever. What's that? Yeah. So we did a bunch of stuff, and what I encourage you to do is to grab the code and go do it, right? Especially the stuff in the first part, and the second part is more about highlighting some of the friction points and how to deploy a stateful application. So we looked at disk topology, resource limits, we looked at the backups and things like that, and how to do upgrades. So a lot of like day 2 operations for running SQL Server instances. And then, globally we covered a whole bunch of stuff. So hopefully y'all know what Kubernetes is by now, and the fact that I can write code to describe what I want and consume the resources of my data center, whether it's network or load balancing, storage, or scaling pods out across multiple multiple nodes in a cluster. Looked at architecture and scheduling and things like that, and how to deploy both stateful and stateless applications. I wrote a book, as I promised. If you want to have a whole bunch of nerdy fun about that, shoot me an email. Maybe I get you a copy of the book. That's cool. I don't know. So yeah, there's my email there. I'm on Twitter a whole bunch. I blog a whole bunch. GitHub. So this presentation will be there in a few minutes, and I'll be sure to put it into the conference's GitHub repo. And I have a whole bunch of content on Pluralsight. 30 hours of this, about 20 hours of that, and about 15 hours of that. If you want a free access code to get into that content, please hit me up, and you can have access to all of that. And I appreciate y'all coming. Thank you so much.